All right, so far in this unit, we've covered like 3 things, okay? We've covered the things that affect the period of a simple harmonic oscillator. That would be a mass on a spring or a pendulum, okay? And that is these 2 formulas here, right? Where T equals 2 pi times the root of L over G. That's for a pendulum. Length and gravity are what affect the pendulum. Okay, and then this one is for a mass on a spring. 2 pi times the square root of mass over spring constant. Okay, so we've covered those 2 things. The second thing we covered, well, that's like one thing, but it's 2 formulas. Okay, the second thing we covered, we talked about yesterday, and that is Hooke's law. That tells us about the restoring force that a spring or any other elastic object is exerting based on how stiff that object is, its spring constant, and how far it has been displaced from its resting or equilibrium position. And then the last thing we covered yesterday was the law of conservation of energy, which actually isn't new. All we did was add to it that now potential energy can be elastic and is related to Hooke's law, the force times the distance, actually the average force, that's where the half comes from, times the distance that it is stretched or compressed, okay, and that gives us the formula for elastic potential energy. So question on the board here is, I will spoil it, 2 steps. That's as far as I'll spoil it, okay? You're going to have to do 2 of these things in order to fully solve this question. All right, so what we have is a mass on a spring, so that's pretty much going to take that formula out of any use to you today, or at least for this question. Okay, it's a mass on a spring, and it's oscillating with an amplitude of 12.25 centimeters, which is kind of a jerk move. What do we always want it to be in? Meters, so you'll have to do that conversion. Okay, and has a maximum speed of 5.13 meters per second. The spring constant is 5.03 newtons per meter. They want the period of that system. Okay, so look at your givens, look at what you have, and the things that we have covered, and see if you can find the 2 steps you need to do to get to the period of the mass on a spring. Okay, give you a few minutes with that. Okay, what is it that this thing has that's the same at both its maximum amplitude and maximum speed? Okay, yes, its mass is the same. Wasn't what I was thinking. It's energy. Its mechanical energy is the same at both of those points. So your first step is a law of conservation of energy question. Here, at its maximum amplitude, it would only have elastic potential energy because it isn't moving there. The spring has been slowing it down all the way there, okay? But all the same, it has been stretching that spring and putting elastic potential energy in it. Here, at equilibrium, is where it would be moving at its maximum speed, and all of its energy would be kinetic. All right, so I can start out with that my initial mechanical energy equals my final mechanical energy. My initial is all kinetic, or sorry, is all potential, so I'm using the amplitude here to indicate that. And at the equilibrium position, it is all kinetic, so I'm putting max in front of the V to denote that I'm at equilibrium and I don't have any potential now. Okay, I need to solve for what? What do I need to get from this calculation for the other one? Mass. Yeah, it's the thing I don't have in this question. So I'm going to cancel the halves, and I'm going to divide both sides by V max squared, and that will give me my mass. All right, so mass will be, the spring constant was 5.03, okay, times the amplitude, which was 0.1225 squared, divided by the maximum speed, which was 5.13 squared. All right, so that's going to give me the mass. Oh, I forgot to start my calculator. What does the mass come out to? Who has it? Clay?
0.00286.
Kilograms? Okay. That seems about right. Okay, so now that I've got the mass, now I can go back to this formula because it's what I was missing, okay? And plug it all in here. So T equals 2 pi times the root of 0.00286 kilograms divided by the spring constant, which they gave me and I already used once, 5.03. Okay, so we'll have 2 times pi times the square root of 0.00286 divided by 5.03. All right, so that should give me a period of 0.15 seconds. Would make sense. That tiny mass would not make that oscillate very much, but it seems a little small. Just going to double check that mass just to make sure.
I got smaller.
You got smaller than that?
I got like 2.87 times 10 to the power 5.
Okay, so 5.03 times 0.1225 squared, and divided by 5.13 squared. Yep, so that's the right mass, so this is the right answer. Okay, it's just really small. Okay. It is a pretty stiff spring for such a small mass, so it's going to move pretty quickly. All right, everybody okay with that one? Would that be a fair question on an exam? Yeah, especially a final. It tests 2 things in 1 question, shortens the final, and fewer questions. So it makes you do 2 things from the unit in 1 place. All right, anybody need that anymore? Okay. Okay, I would like you guys to do question number 1 for sure, because it makes you do basically everything we've talked about so far in the unit. Let's say 1 and 2 for now. We'll leave the vertical spring stuff. So 1 and 2 for now. Okay, like you guys working on those. The answers are right here, so you can check them, and then we'll walk through them here in a minute or 2. Okay, so for part A on number 1, let's write down our givens first. Okay, we know the mass, okay, is 2.50 kilograms. All right, we know that the amplitude is 0.800 meters, and we know that the spring constant is 40 newtons per meter. They want to know the acceleration. Well, if I have the mass and I have K and I know how far from equilibrium it is, okay, could I say that since this is a horizontal spring, that the force in the spring is the only force acting? Is that a safe assumption? Okay, so then I can say that negative K times X equals M times A. If I'm looking for the acceleration here, then I just divide both sides by mass and plug in my numbers. So I'll have negative 40 times 0.8 divided by 2.5, and that will give me the acceleration. Now, they did not tell me which direction the amplitude is in. Okay, so all I can do is give a scalar, is just give a magnitude for the acceleration because I don't know which direction that amplitude was. Okay, my acceleration will come out negative because I'm plugging it in positive. All right, so negative 40 times 0.8 divided by 2.5. All right, so we're looking at negative 12.8. Whoop, did I punch something in wrong there? It's what? Oh, at 0.3 meters. That's what I plugged in wrong. I didn't finish reading the question. There's a lesson. Finish reading the question. You'll get it right a lot more often. All right, so negative 40 times 0.3, not 0.8, and then divide that by 2.5. That's better. Okay, so I'm getting negative 4.8 meters per second squared. That's all I can write. They don't really, I can't really be sure of that because they didn't tell me which direction the displacement was, but that's all I can do. Everyone all right with that? Okay. The only formula we have used, or the only place where speed has been part of this, has been in energy. conservation of energy. That's the only way we can calculate the speed of the object with this information. Now they do want the maximum speed, which occurs at the equilibrium position. Now they also give me the maximum amplitude, which means I can calculate the potential energy there, which is also the mechanical energy of the object. So part B ends up being one of these, just like the first one that we did. We'll have 1/2 Ka squared equals 1/2 mv squared, and that'll be the maximum, right? The halves will cancel, and then we'll divide by m and square root to get our maximum speed there. So we'll have, spring constant was 40. So we'll have 40 times 0.8 squared for the top, divide that by 2.5 kilograms, and then square root that. All right, so we're looking at 3.2 meters per second as the maximum speed for that object. All right, then it wants the period of it. Well, it's a mass on a spring, so T equals 2 pi root m over k. We have all of that stuff, so we just have to plug the numbers in. All right, so 2 times pi times the square root, okay, of 2.5 divided by 40. Okay, so it's going to be 1.57 seconds for the period there. Okay, everybody all right with those? How many people have done the second one? Okay, do we want any more time on the second one? Okay, give you another minute on the second one. Okay, what kind of a question is number 2? Right, it's a Hooke's law question. Okay, you've got that you know the acceleration, okay, and you know the displacement, and you know the mass. It's the only way for you to get k there, okay, is for you to use Hooke's law by saying that the force in the spring is the net force. Okay, with those givens, that's all we can do. Right, so negative k times x equals m times a. We're solving for k, so k will be m times a over negative x. Right, so we've got the trick on this one is that they give you the mass in grams. Okay, so that's 0.0026. Okay, times the acceleration, which was 20. And then we divide that by negative 0.7. Right. Now, is my k going to come out negative the way I have this written? Can k be negative? It cannot. But there's no way around it here. I didn't get any directions on anything in this question. Right? I just have to understand, pause, that k can't be negative here. Right? That's what I have to do. I just have to understand that I'm going to get a negative number, but k can't be negative. That's all right. So when I punch all that in, okay, I got 0.0026 times 20, okay, and then we divide that by 0.7. I'm not even going to bother to put the negative in, right? And that's going to give us a k of 0.0743, which is very, very small. That is an exceptionally light spring. All right, how are we feeling about these kinds of questions? Okay, the trick here is obviously not the math of any of these. The math of all of these is quite simple. Okay, the challenge here is identifying, am I using Hooke's law? Am I using conservation of energy? Am I just being asked to find the period? Okay, because, I mean, the period ones, those are pretty obvious, but the Hooke's law and the conservation of energy, you get a lot of the same givens for those. Okay, the thing you have to recognize on which one you're using is conservation of energy always has to give you information about 2 places so that you can set EI equal to EF. Hooke's law only has to tell you about 1 position. Okay, you're only ever going to use Hooke's law for 1 spot. Okay, and so it's easier to tell that one. Okay, plus you don't usually get acceleration in a conservation of energy question. All right. All right, I want you guys to work on the ones that are in the workbook here. I'll tell you which ones I want you to work on here. All right, I would like you guys to do, whoops, I won't grab the board. 6, 7, 9, 10, and 11. Okay, you guys can work on those. Okay, and we'll go through any that give us trouble here. I'll make that a little bigger.